all, welcome back to another round of chemistry notes. In the last video, we talked about what orbitals are. We learned that they are basically just regions in space arranged around the nucleus where you're likely to find an electron. They're like fancy orbits. Where are you going to find electrons? In this video, we are going to talk about exactly how electrons fill up those orbitals because it is very, very organized. Remember that a subshell is when you have a number and a letter together. So this is the 2s subshell and this is the 3d subshell. It describes all of the orbitals together that have that same description of the same energy level and the same shape. So remember that each subshell has a different energy. So this is energy here on your y-axis. Your 1s subshell has a really low energy. And then 2s is slightly higher, 2p even higher, 3s, 3p, 4s is actually next. If you see 3p and then 4s, 3d is higher, and then 4p is the highest. Each subshell has a slightly different energy. That's going to be really important as we're going over these 4 rules to remember, and you need to remember them in order. So our first rule is the Aufbau principle. The Aufbau principle says in the ground state, which so far we haven't learned anything besides ground state, assume everything is in the ground state until you're told otherwise. In the ground state, an electron will occupy the lowest energy orbital that can receive it. Put more simply, electrons are lazy, right? And Aufbau, this is German for building up. So what this means, with respect to our diagram we just saw, is that this lowest energy 1s orbital, electrons are much more likely to fill this up before they fill up the 3p or 3d or 4p orbitals. They're lazy. This is like a staircase and they don't want to climb this staircase unless they really have to. So we'll see what might make them have to climb the staircase. Rule number 2, Hund's rule, says orbitals of equal energy are each occupied by 1 electron before an orbital is occupied by a second electron. That's the first half. What this essentially is saying is that electrons are selfish. Electrons hate sharing. They will only share if their options are share or climb those energy stairs. They will share if it means they don't have to climb the energy stairs. So that's the first part, is that electrons are selfish. The second part is that all electrons in singly occupied orbitals must have the same spin. We'll talk about what spin means in a second. For right now, it's just how they behave. So if they're not sharing, if they're all in different orbitals, so say we had an electron in this box, and in this box, and in this box, these are your different orbitals. All of these electrons would be behaving the exact same way. They would all have the same spin because they're in different orbitals. So put another way, electrons are followers. Right? They're just going to follow what the electron before them did. This rule is also called the good mother rule. And it's called the good mother rule because whoever named it this, it's called this, decided that no good electron mom would make her little electrons share rooms if they didn't have to share a room. Electrons are selfish. They don't like to share unless they absolutely have to. Rule number 3 is the Pauli exclusion principle, which says no 2 electrons can fit into the same orbital with the same spin. So electrons are a lot of negative things, right? They're lazy, they're selfish, they're followers. What they are not, they draw the line, they are not identity thieves. Right? They will copy each other all day long if they are not in the same room as each other. But as soon as they are sharing a room, as soon as they're in the same space, they will have different behaviors. They will not be identical in every way. So this spin, this behavior, is indicated by an arrow. You can draw a full arrow like that, or you can draw a half arrow. These both indicate spin up. That is one of your options for spin. The other option, because you only get 2 options, is spin down. And again, you can draw that with a full arrow or with a half arrow. I'm going to give you a vocab word that we're not going to talk about until a later date, but for right now you can at least know it. Pauli exclusion principle is the same as saying that no two electrons can have the same four quantum numbers. This is going to make a lot more sense a little bit later on, but for right now, just keep it in your mind. No two electrons can have the same four quantum numbers. Your fourth rule is the Heisenberg uncertainty principle, which doesn't actually affect how electrons fill orbitals. It more just describes their behavior in general. It says it is impossible to determine simultaneously both the position and the speed of an electron or any other particle. So put another way, electrons are wily, or you could say they are sneaky. They're hard to pin down. You can say with relative certainty where they are, but that means you will have no clue how fast they're going. Or you can say with relative certainty how fast they're going, but it means you will have no clue where they are. You cannot tell both at the same time because they're so tiny and they move so fast. All right, so let's see this in practice here. Remember, your 4 rules that affect how your electrons fill orbitals. Electrons are lazy, selfish, followers, and not identity thieves. So let's do an example with carbon. Carbon has 6 electrons. Right, this is carbon. Carbon has 6 electrons. So to figure out how those electrons are going to fill up our different orbitals, because each of these boxes here is an orbital, to figure out how we're going to fill each of these orbitals, we're going to follow our 4 rules and we're going to do it in order. So here comes my very first carbon electron. It's going to start at the lowest energy because electrons are lazy. And there's an open spot for it right here. Orbitals are like rooms. Here's an open room at the bottom of the stairs. This electron is not going to climb any stairs. It's just going to fill in right there. First electron is happy. And then here comes my second electron. And it is here at the bottom of the stairs. And its options are to share this 1s orbital or go to the 2s orbital. Well, it doesn't really want to share, but it really doesn't want to go up the stairs. So it's going to share an orbital here. Our second electron is also going to go into the 1s orbital, but it's got to act different if it's going to share the same room, so it'll be spin down. Then here comes my third electron. Well, now this 1s orbital is full, right? It can only hold 2 electrons. So my third electron is going to go into 2s. And then here comes my fourth electron, and it will go into 2s, pointing the other direction. These are getting out of control. Here comes my fifth electron. Well, 1s is full and 2s is full, so I guess it's going to have to go to 2p. So it'll fill in this first orbital here in 2p. Notice that all 3 of these 2p orbitals, notice that every orbital in my 2p subshell has the same energy. So here comes my 6th electron. There's no room in 1s. There's no room in 2s. So it's going to go to the 2p level. But instead of sharing with this electron here, it's going to go into this second orbital. And since it's going into the second orbital, where it's in its own space, it's going to be a follower. And it's going to take on the same spin as the electron that we just saw. So this is what the electrons in a carbon atom will do. They will be lazy first. They won't go up the stairs unless they have to. They will only share if they are forced. Like here, they're not going to share because they don't have to. They're going to follow when they're not sharing, but when they are sharing, they are not going to be identity thieves. So this is sort of the pattern you will use to help fill in electrons to your orbitals. Let's talk about your orbitals. Let's talk about the order the energy goes in. Because you are going to have to know the order your orbitals fill up. You're going to have to be able to write that in order. But remembering the order is easy. You can just read your periodic table like a book, top to bottom, left to right. What that means is you will start in the very top left corner, and you will read 1s. and you'll read all the way to the end of that line, which there's nothing over here, so the whole line is 1s. If you look back at our diagram, that was the first orbital we filled because it was the lowest energy. After 1s, we've read our first line, so we'll wrap around, start reading our second line, and that is 2s. And if you look back at our diagram, the second orbital we filled, the second subshell, was the 2s subshell. So then we'll keep reading this line all the way across. Here it goes through 2p, right? And that was the next subshell that we filled. It went 1s, and then 2s, and then 2p. And then you've reached the end of this row, so you'll wrap around, start the third row, 3s, keep going, 3p, finish that line, wrap around, 4s, keep going, 3d. So this is weird. Notice that it's true for all of the d orbitals. If they're in the fourth row, they are 3d. If they're in the fifth row, they are 4d, sixth row, 5d, and seventh row, 6d. That's a little weird. And then our f orbitals, remember, go in right here. So if we were to read the sixth row across, it would read 6s, 4f, 5d, 6p, which is a little awkward. All of the orbitals are in the same place we said they should be in the last video, right? This is your s block over here, your p block, your d block, and your f block. Everything is in the right place, but the numbers are all messed up. So let's see why that is. Let's talk about this energy level funny business. So near the nucleus, your energy levels are far apart. Remember, the energy levels that are near the nucleus are the low energy levels. So n equals 1, n means energy level. N equals 1 is the lowest energy level. It's your first row on the periodic table. It's that lowest energy, close to nucleus energy level. And then 2 is higher energy, 3 is higher, 4 is higher, 5 and 6. It gets higher and farther from the nucleus. Near the nucleus, they're real far apart. So like 1 and 2, the closest ones to the nucleus, these are so far apart. There's lots of room between these energy levels. 5 and 6, really far away from the nucleus, these are really close together. They're like almost touching. These are very, very close. So as you get farther from the nucleus into those higher energy levels, they get closer together. So remember that each energy level has some sub-levels in it, right? Your second energy level has an S sub-level that comes down. It's got a P sub-level that goes up. Your third has an S that comes down and a P and a D that goes up, and then S and P and D and F. So what happens as these energy levels start to get close together, their sub-levels start to overlap. So we still have our first energy level with just its 1s right there. And then we have our 2s energy level where 2s comes down and 2p goes up. And so far everything is making sense. 1 is the lowest, and then s, and then p of the next energy level. And then we have our 3s. Where you have your 3 energy level, S comes down, it's the lowest, P is a medium energy, and then D is highest in energy. So that gives you your 3S, 3P, and 3D energy levels. But this is where the problem happens. Once you add in your fourth energy level, that 4S is lowest in energy. It comes down below your 3D. And then 4P comes down, but not so low that it does anything weird. 4D goes up, and then 4F is even higher. The issue shows up right here. Technically, 4S should be higher in energy than 3D. 4 is a bigger number, it's a higher energy level, 4S should be higher. But because our energies are so close together and our sublevels are overlapping, 4S is actually lower in energy. And since it's lower in energy, it's going to fill up first according to the Aufbau principle. Let's do some practice with this. All right, question number 1 here says, how do the energy and the most probable location of an electron in the third shell of an atom compare to the energy in the most probable location of an electron in the first shell of the same atom? So remember, shell means main energy level. It's talking about the number. It's talking about that main number. So choice A says, in the third shell, an electron has more energy and is closer to the nucleus. Well, that's half true. In the third shell, 3 is bigger than 1. It has more energy, but it's also not closer to the nucleus. Choice B says, in the third shell, an electron has more energy and is farther from the nucleus. Well, that looks like a winner because those are both true. Bigger number, more energy, bigger number, farther away. Let's go look at C and D just to be sure. Choice C says, in the third shell, an electron has less energy. That's not true. It should have more energy. And then in choice D, it says, in the third shell, an electron has less energy. Doesn't even matter. That's not true. It's not less energy. So choice B needs to be our answer. Let's look at one more example. Example number 2 says, how many valence electrons are there in an atom of carbon in the ground state? Well, if you go look at your periodic table, go find your square of carbon. So it's got your symbol for carbon with the atomic number and the mass, and then it says carbon underneath it. And then if you look directly above it, outside of the box, there is a 4 above the box for carbon at the top of the table. That is the family number. That's the group number. So this is telling you the number of valence electrons. Carbon has 4 valence electrons. Pretty easy. All right, there is now some practice in your book. There are 8 practice problems. Work through them, do your best, read them carefully. When you're ready to check your answers, go ahead and unpause the video. All right, hopefully this is what you got on your practice problems. If not, you can look on my website to see a more thorough key for a couple of them. Hopefully this is starting to make a little bit more sense. If it's not quite clicking yet, it's okay. It's going to make sense eventually, I promise. You just gotta power through, keep trying, and you're gonna get there. So if you've done your practice and you more or less got it right and you're feeling relatively okay about this, go ahead, start into the next video to get into some practice of arranging electrons. Just over and over, we're gonna arrange electrons, and that's usually when it starts to make the most sense for people, really starts to settle into place. So go ahead, start the next video. You can do it. Good luck. See you there.